Hi, what I have here on the workbench today is a ZOYI ZT-QS7 clamp meter. It was sent to me directly from Zotac. This is a 6,000 counts meter, which is nothing extraordinary, but it is also very affordable. It is so far the cheapest clamp meter I have reviewed on this channel. So for those who are interested, you can find a link in the video description below. Now, don't let the price tag fool you. This meter actually comes with all the features you'd expect from a clamp meter, including the ability to measure inrush current, which some of the more expensive meters don't even have. Also, although it is a 6,000 counts meter, it actually has 6,000 counts across all ranges, including current measurement. This might not be obvious, but for a lot of clamp meters, the advertised counts only apply to the voltage and perhaps resistance and capacitance measurement modes, but not for the current measurements. The actual counts can be significantly lower. Take the 01CM2100B for example. It is advertised as a 20,000 counts meter, which is not wrong, as the voltage range, for example, does have 20,000 counts. But if you switch to the current mode, you'll realize that you've only got 2,000 counts. And just to give you some perspective on its size, here I have the ZT-QS7 next to the 01, and you can see that it's actually quite a bit shorter than the 01. It's a little bit wider than the 01, but not by much. The jaw opening also is larger compared to the 01. Obviously, it can accommodate slightly larger diameter wires. So in this video, let's take a look at the functionalities this meter offers, and towards the end, we'll open it up and take a look inside. Like all the cheap meters, the case is not rubberized, it's just plain plastic. So I would be a little bit more careful not to drop it too often, especially onto concrete floors. But that is to be expected. Now, the first thing I have some complaints about is actually the dial. Now the switch you can see is very stiff. It's not very easy to turn with your thumb, but that's okay as long as it's durable. It definitely feels pretty sturdy, so no issues here. Another minor issue is that it has this indent on the dial. Presumably it is for your thumb. Now, I have seen other meters do this, as some people prefer rotating the switch by pressing down from the top instead of rotating on the side. The issue here is that, as I just mentioned, the switch is very stiff, so you can't press it hard enough to get enough traction to rotate the switch. You just can't do that. You have to do it from the side. And then it's also confusing. You see, here we have a tiny black dot on this black dial. That's telling you where the current range is. But because of this indent here, you might think that actually the range currently is pointing this way. When I first got the meter, I was trying to turn it counterclockwise, but I couldn't. Of course, I figured out where the actual indicator is rather quickly, but the indent here just adds unnecessary confusion. Anyway, this is just something minor and might not bother everyone, but I thought I would point it out. Let me put on some stock leads and then we'll do some voltage measurements. Oh, by the way, the meter also comes with a soft instrument pouch, and you can carry it around your belt. Now, of course, the meter also comes with this lanyard I had already put on. Alright, here are the stock leads. The cables are relatively soft. Now, these shrouds are standard on all leads. I usually just take them right off as they're meant for Cat 4 testing, and for lab use, it's mostly Cat 1 and Cat 2, so we'll take them off. And you can probably see this already, the tips are not gold-plated, which I'm not expecting in this price range. But for a clamp meter, I typically won't use these anyway, as I'm just using the clamp meters to measure current. Alright, the leads are in. So now let's do some voltage measurements using my EDC216A DC voltage standard. And I think we may still have the protective film on. Let me try to remove it here, because it's reflecting the light here. Yep, it is definitely on. So let me do that. And I think you can see it better now. I had to prop up the meter just a little bit as I realized you couldn't quite see the readings here. Anyway, so you can see in the voltage DC measurement mode, we have a resolution of 0.1 millivolt. So let's actually check that out. So I'm dialing in 0.1 millivolts. Yeah, you can see that we registered that. 0.2. No problem. 0.3. So indeed, in DC voltage measurement mode, this meter has a 0.1 millivolt voltage resolution. So now let's just go to 0.1 volt at a time. 0.1, 0.2, 3, 4, 5, 6, 7, And you saw that we lost a digit because this is a 6,000 counts meter. 8, 9, and 1 volt. No problem. Let's do 1 volt at a time. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So you can see that the measurement accuracy is actually quite good. And by the way, this meter is also very intuitive to use. If you have used any other multimeter before, you can pretty much figure out everything without having to refer to the manual. By the way, if you prefer, you can do manual ranging as well by pressing the range button. You can see here, if I press the range button, you will range through different ranges here. Of course, if you want to go back to auto ranging, you just press and hold the range button. So I think for the remainder of the test, I'm going to just use auto ranging. Now let's take a look at the AC range measurement. And to switch to AC mode, you just press this select button. And now it changes to AC voltage measurement. And for this AC voltage measurement, both the ZT-QS7 and the UT61E Plus are measuring the output from a variac. So let me dial up the voltage, and let's observe these voltage readings. And you can see that the update rate on the QS7 is actually pretty fast, roughly on par with the UT61E Plus. And the readings largely agree with each other. Let me stop right now. You can see that we're essentially having the same reading. And let's dial it down. I just realized that we have this rail and peak. You can see here this button in the middle. And if I long press it, it should tell us the peak reading of the voltage. And I assume it would be when we switch on to the range what the peak reading is. Let's actually give it a test. No, it is not. I actually don't know what peak reading it was referring to. Let's actually try it again. So let's switch to a different range and come back here. And AC voltage. Okay, so now it's 25 volts. So now let's change the output voltage. So I'm just gonna randomly adjusting it. Okay, so now let's go to the peak. 61. Okay, so you can see here that it's capturing the peak voltage within a certain time window after switching to that range. Anyway, so that's the rel peak functionality. And if I press the select and range button again, it will change to frequency here. And that's our mains frequency. Let's take a look at what Unity says. Again, you can see that the measured frequency is pretty much the same. Alright, now let's measure a few resistors. And let's first zero it out. And because this is not gold plated, you can see the number is jumping all over the place. But actually it's already 0. But assuming you need to zero it out, you just need to short press the rel button. Alright, so let's first test a 100 ohm precision resistor. This is a 0.1% tolerance resistor here. Yeah, you can see the reading is all over the place because the probe here. And you can see that it's jumping quite a bit. That's because of the contact, but we are getting a stable rating of 99.5, which is definitely out of tolerance. And of course, the leads are definitely not ideal for this type of small resistance measurement. So let's take a look at a 1.25 precision resistor, and this one has a 1% tolerance. And you can see that the reading is pretty much spot on. And let's measure a few more. It's a 10K. And here I think we have a 1 meg. Close enough. You can see that measurement speed is not the fastest, especially if we try to zero it out. It does take a few seconds, but that performance is quite comparable to other multimeters we have tested. And now let's test out the next range. This is continuity. You can see that it's not the fastest, but it definitely is latched, and that's no problem at all. Alright, now let's take a look at the diode measurement mode. And by the way, this meter uses two AAA batteries, so the maximum voltage is 3 volts. So I'm actually curious whether or not this can actually handle a white LED here. So let's jump directly to that. This is a white LED, and let's see if we can light it up. And we are able to, you can see here. Not only are we able to light it up, we're able to also show the forward voltage drop. Very good. Next, let's take a look at the capacitance. And we don't have any residual readings. That's very interesting. Okay, so let's try a 22 picofarads capacitor to see if we can measure that. Okay, it is actually measuring about 27 picofarads. It's still increasing, I'm not sure why, but let's actually do it again. Maybe it's just the way I'm holding it. So let's see here. Okay, so of course you are going to have a lot of errors. It is nevertheless able to measure a small capacitance. Now let's jump directly to a large capacitor here. So this one is a 15,000 microfarads capacitor, and let's give it a go. And you can see that the measurement speed is relatively fast, and the result is pretty close. Now let's take a look at the current measurement. This is a clamp meter after all. So right now I'm using the Unity UT61E, connecting that to the output from my Unity UDP3305S power supply. And the power supply currently is outputting a 10 milliamp current. And now let me change the meter to current mode. And that's AC, let's do DC. So you can see here we have also 1 milliamp resolution. So in theory we should be able to measure that 10 milliamps, but of course we have a lot of offset. So let's actually try to first zero it out. So let me do this. Let me actually turn off the current output, and let's do this. The residual right now is 8 milliamps. So let's zero that out. And let's turn on the output. And you can see that we do have some offset. And that's to be expected, as we do have some variation in terms of current measurements, depends on where the conductor is with respect to the jaw opening. Anyway, so let me increase the current here, and let me see if we can make it easier for you to see. So now let's change the current to, let's say, 100 milliamps. And we're measuring 106. So now let me change it to amp range, and we'll take a look at higher currents. And let's first zero it out. Okay, turn on the power supply. Let's go to 1 amp. And you can see that the display is very close. And let's do 2 amps. 3 amps. And let me change it to 4 amps. 5. And 6. And let's crank up the current even higher. Actually, let me first turn it off. Let's switch to the 60 amp range. And let's change to AC again. Route it out. So now let's turn on the output again. You can see that we are actually about 240 milliamps out, even though we're currently outputting 6 amps. So interesting. Let's increase the output current again. Let's do 7 amps, 8, 9, 10. So it appears that the 60 amp range is consistently out. You can see actually by quite a bit. I'm not exactly sure why. Let's actually turn off the output, see if we're still in calibration. And we are. And you can see that we're within 10 milliamps. So yeah, so not sure why. So let's do it again. Now we are setting to 10 amps. And the measured output is only 9.68. So definitely, I think Zotac needs to look at this as to why the 60 amp range is quite a bit off. Alright, next, let's take a look at the AC current measurement. For that, I'm comparing the measurement results with my O1 CM2100B. And apologize to the angle here, as it might not be the easiest to see. I'll do my best. Now, let me adjust the Variac output. By the way, I have a heater at the output of the Variac, so I can draw some current here. And you can see that so far the readings are largely agreeing with each other. The readings on the QS7 is ever so slightly higher than the readings reported by the CM2100B. And let me actually change it to a higher range here. So let's increase the voltage. Now the current reading has stabilized. You can see that indeed the measurement from the QS7 is about 100 milliamps higher than what is reported by the CM2100B. Now let's take a look at the Inrush current measurement. On this QS7, to get into Inrush mode, all you need to do is go to the current measurement range, and of course it has to be in AC, and you just press and hold the select button. So now we're in Inrush current mode. For comparison, I'm using the Kaiwitz HT208D. Anyway, now I'm going to start the electric drill. By the way, it will be loud. I'm going to warn you. 3, 2, 1. And you can see that there's some discrepancy between the measurement results. On the Kaiwitz we get 14.38, whereas on this QS7 we get 13.6. So let's do that again. Alright, ready? 3, 2, 1. And again, you can see that on the QS7, the reading is about 1 amp lower than what is reported on the HT208D. The meter also comes with a thermocouple you can use to measure temperature. Let's give it a test. And you can see that it's fairly basic. It does give you the readings. And of course, you can, I would imagine, you can change between Celsius and Fahrenheit. Yep, you can do that. Of course, the next function you can see we do have the non-contact voltage detection, so let's take a look at that. And you can see that we're able to detect the live wire here with no problem. In my opinion, the sensitivity of this NCV detection is just about right. You can see that if I move close to the live wire side, it beeps more rapidly, and if I move it away from it, it beeps less rapidly. So that's definitely a very useful feature. I forgot to mention earlier that on the side we also have this button is for hold and also enable the backlight. If you short press it, it will hold the display, and if you long press it, it will enable the backlight. Alright, it's now time for the teardown. And here is the battery compartment. For the teardown, I don't need to remove the batteries, but I just want to show you that it's using 2 of these AAA batteries. There are only a couple of screws holding the backside in place, and if you take a look, you will see that we also have 2 pieces, that these are the side panels, and they are clipped on, and I don't think I need to remove them, but if you pry on it, I think they will come right off. Let's actually first take a look at the current consumption. And you can see that we're drawing about 6 milliamps, which is nothing. And let's change to different ranges. It seems that the current draw is quite uniform across different ranges. Anyway, as you can see here, we actually don't have a whole lot going on, which is pretty much what I had expected for a cheap meter like this. The input protection is actually minimal. You only get 2 of these PTCs, and there's no MOVs at all. The bottom side of the PCB connects to the screen, and if you look at the footprints here, I don't see anything that suggests there's any additional component on the other side. Now, I do want to point out one thing here. You see that Zotac used 2 resistors in series for the input, and these 2 resistors share the input voltage. They are distributed evenly across, and this is actually a common practice. However, if you look carefully, the distance between this resistor and the input jack, by the way, this is a positive input, they are actually pretty close. For typical Cat1, Cat2 measurements, it probably doesn't matter. But if you're going to do Cat3 or Cat4 measurements, and if the circuit board is not clean, a transient could arc over between the terminal and this resistor, and the result could be catastrophic. I'm not saying that the scenario I'm describing is likely, but it's definitely a possibility. And that's why I would only use a high-end, trusted branded meter for Cat3 and Cat4 measurements. With that said, even with the minimum protection this meter has, handling Cat1 and Cat2 measurements, which is probably most hobbyists would do, should be more than sufficient. The digital multimeter chip used here is a chip-on-board design, and I can't tell which chip they're using, but 6,000 counts chips are a dime a dozen. Further down here, we have a 24C08, which is a EEPROM, very commonly used along with the DMM chip to store settings and calibration constants. And the 2 chips up here are marked as 85002, and they are dual 1 MHz op-amps. And the current sensor comes in with this flat flex cable, and you can see we have a trim pot here. Presumably that is used for tuning the 0 DC current reading. We also have another trim pot up here, but I'm not sure what this one is for. Anyway, I think that's all I wanted to cover in this video. Given that this is such an inexpensive meter, and it has Inrush current measurement capability, I wouldn't mind including it in my toolkit. Although some of the ranges are a little bit off and the accuracy could be better. All in all, nothing fancy and nothing surprising in a good way. I hope you enjoyed the review. If you liked the video, please remember to give it a big thumbs up and don't forget to subscribe to the channel for more videos like this in the future. Your participation makes videos like this possible. Thanks for watching, and I will see you next time.